So welcome back. Finally, we are here at the step two. Sorry for the delay because it took a lot of time because I've been working on 10 years of data. So it is taking so much of time for each step. Now, I'll just explain you till the end in this video. And by the end of video, I'll also give you the extraction script and also the user manual which I personally made it. So it can be useful for you. So you can directly copy paste the commands into your drive or your terminal and then you can run everything. So let us start the video. So here I am running the step two, that is unpacking the secondary SLCs. So we have completed the preparation of the reference equation. So now we are running this step two. In this step, ISCE2 will be processing the secondary Sentinel-1 SLC acquisitions. These are the equations that are eventually be compared with the reference equation to measure the changes in the radar phase over time. Oh, so this will also take some time. So I'm just recording only till and then I'm showing you the next stages. So then the video won't be so long. And the purpose of this unpack and preparing in a form that it remains top stack processing so that it can be used for the next stages. So here we are not generating the interferograms yet. At this stage, we are simply preparing the secondary SAR data and their associated metadata. Now step 2 is done. Now we are going for the step 3. This is averaging the baseline. So we are typing here bash run files and average baseline. Here in the ISCE2, it calculates the baseline information between the reference and the secondary acquisitions. So in the INSAR, the baseline describes the relative satellite geometry between two acquisitions. This geometric relationship is important. That is because the differences in the satellite positions can affect the interferometric phases. Now we are going for the next step. And for the demo, I used only 10 data sets. So here the processing is going a little faster. So we go for the next step of extracting the burst overlaps. So we say run extract burst overlap. This means this step will extract the common burst uh, regions between the reference and the secondary equations. Then we go for the fifth step, that is overlapping the geographic to radar geometry processing. So here we are typing bash run files and then run 05 overlap geo2 RT. So this will provide the geometric information that is required to determine how the secondary data should be aligned with the reference data. So that is one. If you are having any kind of problem, you just have to check ls minus lh so that we are finding uh, the total configuration of the files, and then we go for this max2 minus depth, which will show you the baselines. Whether the baselines are available or not, you have to check first. And once you have that, then you need to go for the run 5. So in the manual, I already explained everything clearly, but I'm just um, giving you the command so that if you're facing any kind of issue, you please go through the manual and then you identify the thing and then you can go for the solution. If you still can't find it, then you can just let me know in the comments. Then I'll let you know. I've also explained the type of errors I have faced in my processing. So you can also go through that and make it as a reference manual. And we are running the step 5. This will provide the geometric information that is required for the secondary image to align with the reference data. So this is part of the precise correlation process. And in the coming steps, we will go for the interferogram generation. Okay. So based on your data sets, based on your system speed, the processing speed will change. Right now, for my 10 years of data, I'm still in the step 8. So I'm just for the understanding and for your training, I'm just using the small data and then continuing the series. And after that, you can also perform this on your area, and then you can share your experience. And the other thing is, I've also uploaded a video on Nick Asbas, which is another time series technique. You can also check that video, and you'll find out many new things. In the coming videos, I will also explain you about the GMT SAR, and then we'll go for the NISAR products. That is a MOU between the NASA and ISRO. So I'll also go with that one with real-time examples. Now we are running the run 6, that is overlap resample. Now that overlap geometry has been calculated. Now ISCE2 will resample the secondary overlap into the reference geometry. This objective is to bring the two acquisitions into the same spatial framework so that the corresponding radar measurements can be compared accurately. Once this is done, we'll just have to check, and then we need to go for the pairs registration. That is 7th step. At this point, ISCE2 will examine each interferometric pair and estimate the remaining misregistration between the acquisitions. Here, misregistration means same ground location may not fall on exactly on the same radar. I mean, the pixels in two different equations. Even a small misalignment can seriously affect the interferometric processing. So it has to be estimated accurately. That is why we are running the step 7. Once it is done, now we are going for the step 8. It is time series misregistration. Okay, so let the step 7 complete. So the estimated range and azimuth offsets are then used in the following time series misregistration step. That is in the step 8. See, now I got an issue that the matching versus 16 and 17, but there is a problem. And I just have to see. So you please go through the error, what you are looking. Here it says in the problem is in topsStack overlap with dem pi. So what you need to do is you have to just check that first where it is, and also you need to make sure that the path is export. That means the path is linked to your working environment. Now what I am doing, this overlap one initial file, I'm just trying to add that to the path so that there won't be any interruption later. So now I've added the path to this one, and I'll run the step again. So before that, I'll just have to check which loops, because I got the error of which loops here. Because I got the error of which loops, so I'm checking again, and then I'm using the path. Now if I run again, so this will take some time. So you just go through the manual ones, and then you can also have a look of what other errors are you getting it. If I can't get the data, or if I can't get that output, I'll have to check where my files are. So this is not a single time installation, but when you're going for the first time of processing, you will face many errors. But once you are done with the first time processing, and afterwards you don't have to look for this kind of errors again, so you can continue any place, any data. Now I'm working for one state, so I'm having all these errors now. Once I rectify these things, and if I go to the next state with another set of data, then I won't be getting many issues like this. So here I find the looks.py. It is located in the lib. Python 3.11 and in the site packages. So I have to tell the software that the looks is located in this drive. It is home Manik and then site packages ISCE2 application looks.py. So we just have to tell the software to access that. So that is why we are using the command path. So I'm telling export path and then I'm adding the same location and then I say again p locations and then say path. So I'm giving the path now and when I say which looks.py I'll get the path. See, now I have added the path and now I have to run the step again. So files and then run 07 page visit. So you can see now this GDAL and then the VRT win and the files and then bands 1 bit 1385 float. So it is completed. You can see the bad match level 1 and 2 like that and then you have the .vrt files. So this is done and you just have to go for sorry it's bash. Oh, sorry it's ash. So I have to go run the again b. It's just bash not ash. So I have to type again bash run files and we are done with the seventh step. Now we are going for the eighth step. Here eighth step is done. We are just taking the pairwise distribution information from the previous stage and solve for consistent acquisition levels that are offsets across the entire stack. Then we are going for the next step, that is 9. We are going for the full burst. So in the previous stages, ISCE2 is working with the burst overlap, the regions to estimate the relative distribution between the acquisition. Now we have moved from the overlap regions to the full burst data. In this stage, ISCE2 will perform the geometric processing from the full burst stack. In the manual, I have explained what step 9 in ISCE2 is what step in SNAP. So you can understand the traditional methodology of SNAP and ISCE2 both together. Now we have completed the 9 and then I'm going for the next step, that is 10. So I just have to go for run 10 and then if you press tab, it will automatically show you the next step. So here we are now using the geometric information that is calculated in the run 9 to resample the full secondary bus. So the objective is to align the secondary SAR data with the reference equation as accurate as possible. So this is almost done. Then we are going for the next step. So you can see the files here and run 11, bash run 11. So the purpose of this one is this stage will determine the valid common region of the stack. That means the area where the equation can consistently be used together. This is important because the latter interferometric processing needs a common spatial region. So that is why we are running this 11. Once this is complete, the ISCE2 will know the valid processing extent that can be used consistently across the stack. So this is done. Now we are going for the run one, that is merging the reference secondary SLC. So just type merge and then tab. Sentinel-1 TOPS data are divided into bursts and swaths. So the processing up to this point is dealing with the individual burst level products. Now ISCE2 will merge the processed burst information into the required SLC stack representation. So this will bring up the point where co-registered SAR data are ready for interferometric processing. Now we are going for the 13th step, that is generating the burst. So here we are actually generating the interferometric product. So an interferogram is produced by comparing two complex radar measurements from two equations. So the phase difference between two equations contains information about the change in the radar path. That information can include topographic effects, atmospheric effects, orbital effects, geometric effects, and also the surface displacement. At this stage, you see ISCE2 generating the interferograms at the burst level. So if I am going to the folder, I can see I am processing information. I think see the location is MintPy ISCE2, and I have to find the interferogram. There are two ways to do it. One is you can just go manually and then check the files, or you can type the command here in and you'll get the information. See here I can see. So I go for this overlap, and then I see IW1, IW2, IW3. You can check the interferograms again with max depth. Free. Now I have the sorted things IW1, IW2, IW2, IW3 like that. Now we are going for next step, that is merging the interferograms. This is burst diagram. So the interferogram that are generated in run 13 are need to be organized at the burst level. In this, ISCE2 will merge those burst interferograms into a larger interferometric product that is corresponding to the processor scene. At this stage, we have a merged interferogram ready for quality processing. See, now you see the interferograms again. Then you see merge. You want this one. See, it's ISCE2 demo merged interferograms, that folder. Okay, so we can get that merged interferogram. Now we will go for the filtering of the coherence, that is run 15. So coherence will tell us how consistently the radar signals behave between two equations. When we run this, the important outputs from this stage will include a filtered interferogram and the corresponding coherence information. So this is PS filtering right now. We are done with this step. And we are at the last step now for ISCE2, that is run 16 unwrap. This stage is called as unwrapping. The interferometric phases that we obtain from the SAR data is wrapped again, just like we are doing in the SNAPHU, the phase unwrapping stage. We are using that. So here it is using Snap version 1.4.2, which is installed in my PC. So the unwrapping is going on. Then we'll go for the ISCE2 MintPy after this stage. So this is done. It took 96 minutes for me. And here MintPy needs to know where these ISCE2 interferograms, coherence products, connected components, baseline information, and geometry products are located. So here we are using the most important small baseline application dot configuration. This is most important. Before that, we just check our data sets. So we have completed all the 16. So these 16 steps are from the ISCE2. And now we will go to the next steps of MintPy. So here the most important configuration is that ISCE2 processor settings and the path to the merged interferograms and reference geometry. So we are editing the small baseline application dot configuration according to the source data or the data where it is asking. So right now I'm just showing you the folders, the ESD, and then whatever the files we have, because we need to add these details in that configuration file. So you check everything clearly once, and then georeference, then we go for the interferograms. I already added these in the manual, so you can just go through that one also. And then the SLC is with azimuths and the references. And these are the run files which we have used for processing in ISE2. And these are the secondary files. And then now we are entering, like I showed you the physical drives. I'm also showing the commands to find the coherence, interferogram, and everything. So we are just checking this terminals in the terminal ones. So I'm just using the commands which I've already given in the manual. And then we go for the next command, that is finding the post overlap post interferograms. And then you can see next, it's in the ESD folder. And then we are going for in the interferogram folder, we are checking. These are the data. and then the overlap files, and then the interferogram, merge interferograms we are just checking. Just for my four data sets, it's less, but you will have a bigger data. So you will be having many number of files. Now we are ready to go for the editing of that small baseline app configuration file. I'm checking where my small baseline app file is there. Then I had -20 and it is not found. That is because I need to tell a MintPy for the terminal the location of this small baseline app. So here it seems I haven't installed MintPy yet. I think in the previous video I have installed MintPy. So you can just follow that and then install MintPy in the earlier stage. This is because a demo I didn't install that MintPy yet. So I'll install it again. So before that I'll just check Py and then print and then go with the I'm supposed to get the output, but it didn't show anything. I'm just checking what environments I have. So I'm just installing the MintPy and wait. It's done. Now we'll go for the small baseline again. Now I got the location because I've installed MintPy now. And then let us check. And so I got the path. What are the steps involved and everything. So we need to add the working directory. We need to add the locations of everything in this configuration file. Then only MintPy will start doing the processing automatically once you give the command. And then we go for and here you see it is showing you the working directory. So we need to see where it is. And then we just have to, you can do it in two ways. One is you can open that configuration file using the MintPy notepad and then do the editing, or you can go for the nano command in terminal and also you can edit it. So nano small configuration file and enter. Here if you see, it is having every step, load data, and then for ISCE2, then interferogram stacking, ionospheric stacking, offset stacking, and also for everything we need to load the location of the data. Where is the data? We are telling the data that from which processor it has happened. We use ISCE, so we are using the ISCE, and we are giving the auto path as no, and then We are also giving the unwrapping files location, the corresponding files location, connecting files location, and the meta file location, and also the baseline directory. So whatever it is asking, we just have to configure that file properly, the location properly, and then only we'll have to run the commands. So intentionally, I'm just giving some other comments, so you will see what kind of error is really coming. So the XML file is here outside IW123 XML. So I need that reference. So here, if I go to that reference, I just have to go for the meta file. Here I have to add the path, and it is reference, and then go for that IW star. That means it can be 1, 2, or 3. Like this. Again, the same way I'm giving the paths for the other things also in the baseline directory. It's baseline. So if you want to see, you can go to the folder and also see the baselines. It's on the top. So we need to give this path. And then I've already added the interferograms, unwrap, wrap, and power files. So you just use them and then save, and then you have to run. So here we are asking every step, one by step by step, like that. So if you see clearly, every step is mentioned already in the top. See on the top, you see I I have an error here right now, and then I'm using that step again to troubleshoot. That is, we are running and loading the data. So I just have to type the names again and see the path which is properly given. So I haven't given this secondary path. So again, I have to check files and then go for the next find view and then reference type. So when we say do step, that means we are telling MintPy to perform this step. So I have found the georeference files, and then I'm also looking at the georeference merged files. Now we are going with the nano again, and because I skipped some steps. Now I'm adding those steps again, and then just modifying the script. So I'm looking for the geometry in the dem file path. So incident angle and then azimuthal angle. We also need to look at the latitude longitude, but intentionally I left it like that because I wanted to show you the error. If you skip that latitude longitude, what will happen? So we are just telling to load the data, and if you see clearly on the top, remaining steps, modify network reference point till you have velocity and then geocode and Google it. See again, I got this error. Now I have to check back again. So I'm going back. See, this is the whole error what I got. Only at the last point I have this error of running because there is no such directory. That means because I intentionally left the directory, it is not showing. So I have to add that location also. So again, I'll go for the nano, uh, and then I'll go for the finding of the merged reference. Here you have the merge and geo reference and shadow mask and LOS, latitude, longitude, HDR, incline, local, HGT, RDR. Again, I'll go and see here these points I've left. Look up latitude and longitude. So I have to add those locations again. No, again we'll go for the modification. So we see 56, 55, 63, and in this nano, I'll go to that location again, and then here you can see I left those places some at the bottom. This lookup Y file and lookup X file. Here I need to add the latitude and longitude. The location of the files, not those values. So latitude row instead of auto, I can go for the path, that is clear this, and then here, and then it's here in lat.rdr. The same way for the longitude, I need the long.rdr. So merge, it's in merge georeference lat.rdr and long.rdr. I added the latitude, longitude, and then I'm saving it again, and then I'll run again. So these are very important steps. That is why I'm asking you to go for the check every time. HGT, the lat, HDR, long HDR. These are available in the um, physical directory also. So we'll just go again and then load the data. So you can see creating the height, latitude, longitude, incidence angle, azimuth angle. The error which you are seeing in the previous step, it's not occurring now, and it is done. That means the data is loaded completely. And then we'll go for the next step. You see the we got this geometry, small baseline, and then interferogram stack. Now we are going for the modify network. That is the second step. So if you want, you can just have a look at on the top the remaining steps that will tell you what steps to be done next. So you just have to give the command do step and change that step name. So here I see next command modify network, and after that I completed, and after that it is reference point, then quick overview, then correct unwrap error, invert network, like that. So we are going for the reference point step name. So we are telling small baseline APY configuration, do step reference point, and then this doing the reference point. And you see the max coherence, and this step is also done. Next, we are going with the quick overview. Excellent. See, just because I'm using less number of files, these steps are very fast. But when you are using huge number of files, these steps will take a lot of time. And then we are going for the correcting the unwrapping error. Then next is inverting the network. So before solving the time series, MintPy prepares the interferometer network. This network will describe which equations are connected by the interferograms, and therefore which temporal observation can be used to reconstruct the displacement history. So depending on the configured workflow, the relevant stages will be inverting the network, and then reference point, and then quick overview, and then unwrapping error. So here in the network, I have an error. So I just have to see what is error. It says looks. So during the network inversion, this problem is one of the cause. So L looks and R looks. These describe the azimuth and the range. So A look is azimuth and R look is range. So these multi-looking factors are used during the interferogram processing. So in our ISCE2 processing, these values were 3 and 9. So you can just see the values here. When you go down, and then when we check the inputs of the interferogram and see here. So I'll just go to the small baseline, and then I did nano, and then I have changed that values, and I got 9. So I said use 3 and 9, and then I went for the next step is correcting the LOD. And we'll have one more issue with the atmospheric correction, which is a optional one. It deals with the EREF5. So that is one of the biggest step that creates a problem. So if possible, you can just create some EREF5 data, or you can just skip that part, because in this processing session, the EREF5 correction is encountered with the weather data download. Therefore, atmospheric correction should be introduced separately when it is actually required, and when the atmospheric data sources have been correctly configured. So I am going for the next, correct the ionosphere, and then we'll go for the next step of correcting the troposphere. So the ionosphere correction checks whether any appropriate ionospheric correction is configured. In this case, the MintPy reported that there is no ionospheric correction was applied. And after that, we'll have to go for the residual or the topographic correction. So the purpose of this stage is to reduce the systematic components that can remain in the interferometric time series, which will affect the deformation estimation. So I have an error here with the toposphere because I have typed it wrong. It's troposphere, and again I have an error with this. So I just have to check list index out of range, and then I'll have to look for the cost, and then I'm going with the nano again and see what is the problem. So I'm just going now to step to modify interface done, and then we are going the next step. Reference point is done, and then path closure, invert network, and go down slowly, and then here character node done 6, and then 7, and split then 8 to split. We just have to see. Here it says ERA5 is from ECMWF, and these kind of data, if you have, you can just use them or you can skip them. Now I have corrected it and made it none. And then it is not, there is no troposphere delay correction, and that step is done. Now we'll go for the DRAM. DRAM and then enter. No phase ramp removal. And then we go for the next step of correcting the topography. Topography. Just it takes some time. You can see the slant angle and pixel with zero innocutions, non-innocutions, skipping zero temporal coherences, and then crossing patch 2 out of 2. The same steps will repeat. And in the meantime, please do let me know if you are looking for any other kinds of specific videos. I'll be doing that one. And I have a plan to do about the weather forecasting and weather and climate analysis also, because these are responsible for some kinds of disasters like landslides, floods, and all. So, as we are going in that direction, we'll see about those parameters also, how they are going to influence, how to identify the uh, parameters, how to identify the cloud cover, how to identify the chances of thunderstorm. I'll explain you about some models like Cape, Icon, Icon Cape, or others. So we are done with this step, and then we are going for the next step of only residual RMS. Now we are evaluating the residuals of the time series solution. So the residual RMS provides the measure of how much unexplained interferometric variation remains after the model time series and corrections are taken into account. This is useful for assessing the quality of the time series solution. So residual RMS, and after that we are almost there to the end. and we have to go for the reference date and then velocity geocode. So residual RMS is done. Then we'll go for the reference date. So this will just give you a final output, but again we have to use a script to extract the time series from a particular point. So the script which I am attaching, you can just modify according to your work directories, and then you can find out the time series displacement of a particular location, and you can also give the radius and all those things. I'll show you. Now we are going for the velocity. This is the place where the result is spatial velocity field. So MintPy is taking the displacement time series and estimating the long-term deformation rate for each valid pixel. This velocity is generally expressed as a rate of displacement over time, and it is related to the selected reference. Now I have an error here, and I just have to check which one. It is ERA-H5, the one which I'm telling about the weather. So we'll just check again. Here, velocity ERA-5 is not found. So we go to the folder, and then or you can just go for the delete like this. It's in the inputs folder, and the DRA file is gone. And then we go for the next run again. So we have deleted that ERA file. Velocity. So it is done. And then we are going for the geocoding. This the velocity product at this point is still associated with the radar geometry of the processing stack. So to make it easier to use in the JS and geographic visualization, we are using this geocode product. So geocoding will convert the radar coordinates results into geographic coordinates using the geometry and information that is generated during the earlier processing. So we do this, and then you can see the output extends south, north, west, east, latitude, longitude, and then rows and columns. And you can see the latitude, longitude from lookup table. The next last steps are Google Earth and then HDF. So we are creating the azimuth angle, height, incidence, latitude, longitude, slant range, and we are creating the H5 file. These files are very important. Whatever you are getting from the output now, you can take a backup of these files. So in case if you lose any data by the formatting of your system or something, these files can at least help you to extract the time series from any particular time. If you don't have that Sentinel files, or if you don't have that orbit files, if you still have this velocity H5 file and the mask temp coherence files, all these files will definitely help you in backing up your data. So we are looking at the products here, and we just creating the Google Earth KML or KMZ. Once the processing is done, you can see the KMZ also. And the processing depends on how big your data is. So the KMZ file which I have created is for a whole acquisition. So it covers a very huge area, but the points are very few. So I'm getting the data in the in the Google Earth opening. It's very fast, but when it comes to 10 years of data, it will take a lot of time. So for checking, you don't have to open that KML file. You can directly go to the next step, and then you can see the um, data. Or you can, if your system is highly supportive, you can open Google Earth or any other compatible application and see how the velocity is. Next, after Google Earth, we'll just go for the final stage. The best thing about ISCE2 and MintPy is first you do the basic configuration of all the processing in ISCE2, and then give the MintPy a small baseline configuration file, all the paths that are from the ISCE2, and then once you start giving the steps, it will automatically do everything, and it will give you the whole data. So ISCE2 is one kind of processing. There are other processings also, and I'll be uploading the Hype 3 also on demand. So how you will be selecting the files in Alaska ASF and create the request for on-demand processing for the Hype 3 files, and then how you download, and then how do you process in Ubuntu, and how do you get the time series and make detailed videos, and I'll post it in the group in the channel. So you can just have a look at that one also. Now it is preparing the output. Because it's a huge file, it will take a lot of time to write. First thing is the KMZ file is saved, and it is saving the PNG file also. And it is saved. We have the KML, we have the PNG, we have the KMZ. So I have refreshed. You can see that KMZ file, and I'm opening it in Google at once. So you can see that legend on the bottom. It is just because 2 points, it's like this. But when you have hundreds of data sets, it's not easy for opening this kind of data in Google Earth also. Now we are going for the last step. So this is where our time series will be saved. And now I'll show you one script which you can use and extract the data, the result or the time series from a particular location. See, these are the backed up files from my previous project because unfortunately I lost the whole data, but I can only get these files. So based on that, I'm just running the script in the time series file location and I'm able to get the data. So that is why I'm telling you, whatever you backup doesn't mind, but if you are not backing up the H5 files, then it will be a problem. So try to copy those data files. Now I'm using my script extract MintPy site and just running it so that it is reading the velocity H5 file already in the directory. And then I go for Python, and then extract, and then MintPy site, not py. See, because I don't have that KML, so I'm unable to get that one. So I'm installing the pip simple KML. That means I'll get the KML output also if I have that dependency. Now it is installed. Now I'm running it again, and there's the location, and these are the details. I've selected 0.5 kilometers around that point. If you see that KML file, so it is covering 500-meter radius around the center point. These are the points all we get. And after that, if you open the time series and then you plot the graphs using that Excel sheet, you will find whether that place is subsiding or how it is behaving. So please do subscribe to Geoscience Engineering and then please ask any kind of queries and please do watch the other videos also. And thank you for watching.